Hello everyone, my name is Xiaogang Xu. I will present our paper, Deeper Parametric 3D Filters for Joint Video Denoising and Illumination Enhancement in Video Super Resolution. The goal of VSR is to produce high-resolution videos from low-resolution video input. Although results with high quality has been achieved by current VSR method, those approaches typically don't work well on videos such as low light and noisy, but such a setting is very common in practice. Thus, in this paper, we study how to map a low-resolution low light and noisy video to a high-resolution normal light and noise-free video. One direct solution is to use the best network model of each task by cascading models in a certain order. For example, suppose the input LLN videos are donated as XT and the output HNN videos are donated as YT, then the order can be SR, denoising, illumination enhancement, or denoising, illumination enhancement, and SR, and so on. However, doing so has several drawbacks. First, the network complexity is threefold, resulting in a slow inference, and the optimal order of different networks is harder to decide for each thing. Moreover, as the three networks are trained individually, we cannot ensure their consistency. For example, artifacts from a previous denoising or illumination enhancement network could be enlarged by the next SR network. In addition, it is not also difficult to train or fine-tuning the concave models end-to-end, since the current networks often take multiple frames as input and output only one single frame. So a subsequent network cannot obey sufficient input from the previous one. Another approach is to use parallel branches of different purposes in a framework. Different branches produce different mappers or filters to complete different tasks, and they are finally combined to produce final HNN videos. However, such a setting also has disadvantages. First, we until need to infer the different branches to produce the final result, which is time costly. And as the branches are individually trained, the concatenations among different branches are weak for joint learning of different purposes in a framework. Moreover, the input to all branches should be identical, while the size of their outputs are inconsistent, which is harder to optimize. Therefore, how to achieve variance purpose with a common branch and the presentation is worth to be considered, and this is the target of this paper. In summary, in this paper, we have three main contributions. First, we complete mapping LLN videos to HNN videos within a single stage end-to-end network. In other words, this is the first work to achieve video SR, denoising, and illumination enhancement simultaneously. With our designed DP3DF, extensive experiments are conducted on real-world video datasets to demonstrate the effectiveness of our framework. Now we're beginning to introduce our framework. First, we give some notations. XT donates LLN frames, where T is the number of frames, and YT is the synthesized HNN frame with the upsampling factor as R. CT is the intermediate HNN frames, and YT hat is the ground truth HNN. WT is our proposed DP3DF filter. This is the overview of our framework. The encoder branch extracts deeper features from network input XT, and the decoder branch produces the output for learning the deeper 3DF and the residue image RT. We learn the DP3DF for synthesizing the intermediate HNN frame CT. Finally, we reassign CT using RT to produce the final output YT. And the branch for learning the DP3DF and the residue image share the same encoder and decoder backbone. Also, our DP3DF uses adjacent temporal spatial information around each pixel. And in the following, we will introduce the details of how to apply DP3DF to a video. Each pixel has DP3DF kernels, each of size kh times kw times kt plus 1, and can be divided into two parts, which are WTB and LTB. WTB has the shape of kh times kw times kt, which is the weight for denoising. The dimension of LTB is 1, which is utilized for illumination enhancement. For each pixel, DP3DF can obey R times R output pixels to achieve super resolution with upsampling factor of R. And this is the visualization about how we apply the learned DP3DF to process an input video clip. For each pixel XTIJ, we locate its 3D patch and its associated DP3DF kernel, and then make use of the kernel component to process the 3D patch to produce R times R output pixels. And this is the formulation for applying DP3DF. Suppose P is the pixel location of ij. R1 ranges from 0 to R minus 1. R2 ranges from 1 to R. WMNO is the RE times R plus R2's kernel at pixel location OP, where MNO describes the displacement, and the upsampled R times R pixels in CT can be predicted as the following equations. And there are some important details to complete the DP3DF. First, since WTB is utilized for the denoising purpose, it is normalized through softmax, zooming to be 1, and LTB is utilized to adjust the illumination, and according to the Retinix theory, it is processed with the activation function of sigmoid, and we take receptacles. Moreover, the encoder for DP3DF has two downsampling layers, each with several residue blocks and instance normalizations in them. The decoder DP3DF adapts a pixel shuffle for upsampling, which is learnable. Moreover, our DP3DF is indeed a generalized filter that combines the properties of dynamic filters for variance tasks. If we remove the temporal dimension kt of DP3DF and also the dimension of illumination enhancement, then it will become the current kernel for video SR. And if we further remove the R times R output and only have one output, it will become the kernel for video denoising. And if we further remove kh times kw kernel size, it changes to the kernel for illumination enhancement. To enhance the performance, we adapt a residual learning branch to learn a residual image RT for enriching the final output with high frequency details. The residual image RT is produced from multiple input frames, and the residual learning shares the same encoder-decoder structure with the main branch for predicting the DP3DF. This allows us to reduce the computation cost. The final output YT is equals to CT plus RT. And this page shows the training processing of the reconstruction loss on CT and YT. We can see that at the early training stage, their difference is larger and would finally converge to a similar level. And as proved by the experiment, the residual learning can improve the converged result. Now we talk about the loss function to train our framework. The first is the L2 loss term for obeying an accurate prediction of CT as LR. We describe another reconstruction loss for the residual learning branch to generate the final output YT as LE. And we use smoothness prior for illumination enhancement. For adjacent pixels C, P, and Q with similar illumination values in a video frame, their constraint in the enhanced frame should be small. So we define the smoothness loss on the predicted LTM as LS. The final loss term is the weighted sum of those three loss functions where lambda 1, lambda 2, and lambda 3 are loss weight. Now we're beginning to talk about the experiment in this paper. We perform our evaluation on two public datasets with both indoor and outdoor real-world videos. The first is the SMID dataset. The videos in SMID are captured as static videos. Especially, we explore mapping from LLN to HNN frames in the sRGB domain, and convert the low-light videos from the raw domain to the sRGB domain for SMID. On the other hand, SDSD is a dynamic sRGB video dataset, including both indoor and outdoor subsets, and there are paired data. To evaluate the important component in our framework, we conduct 3 ablation studies. The first is the setting without temporal. In this setting, we remove the property of the 3D filters by ignoring the temporal dimension and filtering only in the spatial dimensions. And the second setting is called without spatial, where we remove the spatial dimensions in DP3DF and apply the filters only in the temporal dimension. The last ablation setting is called without residue, which means removing the branch of residue learning. We display the quantitative result in this page. As shown in this table, all ablation cases are weaker than our 4 method. The comparison of hours without temporal, hours without spatial, and hours show the importance of considering both temporal and spatial dimensions in our 3D filter, and the comparison between hours without residue and hours demonstrates the effect of residue learning, since our 4 model until consistently achieve better results. In this page, we show some visual samples proving the obvious degradation caused by removing different components in our 3D filter. There is no work designed for directly mapping LLN videos to HNN videos, so we chose the following 2 classes of workers to compare with. First, we consider a rich calculation of SOTA method for video SR. This table shows the comparison results with SOTA SR method. From the table, we can see that our method consistently achieved the highest PSNR and SSIM for all the datasets. And this page shows the comparison on SMID. The result from our method has a high constraint and clear details. And in the regions with complex textures, it can be obvious that our output have fewer artifacts, so our results look cleaner and sharper than those produced by the others. This page shows visual comparisons on the SDSD indoor subset that feature dynamic scenes. Again, compared with the results of the baselines, our results are better. And this is the visual comparison on the SDSD outdoor subset, which also shows the advantage of our framework compared with the other baselines. Moreover, this is the video-based comparison on SDSD indoor, SDSD outdoor, and SMID dynamic scenes, where our method gives better results on each frame, and also higher visual consistency. This figure reports the run time of our method and other baselines. From the figure, we can see that our method is efficient with very low running time. Moreover, we also compare with the baselines that use network models for video denoising, illumination enhancement, and SR in a cascaded manner. This table summarizes the comparison results with baselines. We can see that our method always produces top PSNR values for all 3 datasets, and our SSIM values stay high compared with the others. Also, we conducted a large-scale user study to compare the visual quality of our method against various SOTA video SR approaches. We randomly select videos from the test sets of SMID and SDSD, compared the results of different methods on those videos using an A/B test. For each test video, our produced result is video A, and the result from some other baseline is video B. In the test, each participant should simultaneously watch videos A and B, and they should choose which one is better. This figure summarizes the results of the user study, showing that our results are more selected by the participants over all the baselines. Thanks for your watching.